Hi, I am Durukan. I am doing a master's degree in electrical engineering from Yıldız Technical University. Today I am going to present a case study to determine the capacity factor and electrical energy production potential in wind turbines. This is my presentation plan. You see here introduction, renewable energy resources, study field, variable probability function, capacity factor, power curves, result and discussion, conclusion, and the final references. The popularity of renewable energy systems is increasing day by day. It is especially important for the goals of European Union to reduce carbon emission to zero and to control seasonal changes. Among these renewable energy systems, the most known ones today are wind and solar energy systems. Wind energy systems are basically systems that capture the kinetic energy of wind and convert it into electrical energy. It is vital to determine the energy production of these systems, and viable probability function is the fastest and best way to do this. Using this function, we calculate the capacity factor and energy production among three turbines of different power in Turkish region. What are renewable energy resources? That the resources that use natural processes for energy production and can renew themselves in a much faster time than the depletion rate of resources used are renewable energy resources. We can evaluate them under 6 main headings: wind energy, hydro energy, solar energy, geothermal energy, bioenergy, and hydrogen energy. If we look at the status of renewable energy resources in the world, there is about 200 exajoules levels renewable energy resources consumption in 2018. However, according to a report prepared by BP, there are three different scenarios created by European Union until 2050. The first scenario is business as usual. This scenario shows that what will happen if the situation in recent years continues. The second scenario is rapid. Is a scenario that show what would happen if carbon emission were to reduce a lot, even if they couldn't be reduced zero, with certain and supports and policies. The third scenario is the main target scenario, is the net zero scenario. In this scenario, it is aimed to reduce carbon emission to zero by 2015. The common feature of the three scenarios is that use of renewable energy sources will increase considerably until 2050. If you look at the net zero, renewable energy sources must dominate the sector in order to reduce carbon emission to zero. If you look at the status of renewable energy resources in Turkey, according to 2001 TEİAŞ data, there are 9,665 power plants in Turkey, and these power plants have an installed power of 97,000 megawatts. Wind power plants have a share of 9.6%, which means 9,360 megawatts of wind installed power. If you look at the advantages of renewable energy sources, there is no risk of runout. It is environmental friendly, and maintenance requirements are low, and consequently maintenance and operating costs are low. And the most important feature of renewable energy resources is that they reduce foreign dependency. Again, if you look at the disadvantages of renewable resources, in the light of these disadvantages, which can be expressed as uncertainty, discontinuity, high investment cost, storage system problems, and geographical boundaries, it is very important to calculate the energy production by wind power plants correctly. Disadvantages such as high investment cost are likely to drive the investors away. However, its uncertainty and discontinuity poses a great challenge, especially for the countries that want to increase the use of renewable energy sources. Discussions arise, such as the amount of energy that should be given to the consumer, or the policies with which energy will be bought and sold. These are problems that can be avoided in certain amount with accurate, consistent calculations. On the next slide, we see our study field. On the map, you can see on the right, our study area is visible. This area is the Terkos region near the Çatalca region on the Black Sea coast of the Istanbul. We obtained the wind speed in this region from the literature. We normalized the wind speed measured from 52 meters to the heights of our wind turbines used in the study using the Hellman equation. Here you see the Hellman equation. H1 is the reference height. H2 is the height we want to measure. That is the height of our turbines. And wind speeds in H1 are Y1 and Y2 are wind speeds in H2. After obtaining the wind speeds, we use the variable probability function to model them. The most important feature of this function is that it is fast and reliable. We see two equations below. The first one is the probability function and the second one is the cumulative probability function. As we have seen in it, the parameter expressed with y is the wind speeds and the c is the scale parameter and k is the shape parameter. The scale parameter and shape parameter are related to the width and the shape of our wind profile, as their names suggest. In the graph you see on the side, we see the result of 5 different functions with the same scale parameters but different shape parameters. And as the shape parameter decreases, our graph resembles a exponential function, while as it is grows, it resembles a parabolic function. Therefore, it is very important to determine the shape and scale parameters properly. We use 3 different methods for this and compare these methods to each other. These are the moment method, energy pattern factor method, and modified maximum likelihood method. And based on this, and after this, we use the capacity factor for compare the turbines. This is very important parameter and can basically be expressed as the ratio of the energy produced to the maximum energy that can be produced. In another case, I can express the generalized formula. As you can see, the first formula is that here: average power output divided nominal power. Based on this, the method of calculating the capacity factor with the variable is the second function. As you can see, our nominal power output is here, and however we need to use variable probability function and wind turbine power output function to calculate the power output we have obtained. And we see here the third formula is power output formula, and if the wind speed is lower than the cut-in speed, and power output is 0. If it's between the cut-in speeds and the nominal speeds, it means a rising function. This region is a rated region, and if it's higher than the nominal speed but lower than the cutoff speed, we get the fixed rated power output. This area is the memorial area. If it's faster than the cutting speed, it is 0 again. For this reason, we need to calculate the non-rated region as a function and put it into the process in this way. Here we see the power outputs of the wind turbines, we used in our study. We plotted power curves for different turbines of 1 megawatt, 3 megawatt, and 5 megawatt, and from these we obtained the function of the non-rated region. In the light of all these information, the results we obtained for 65 meters are around 1.99 in our shape parameter, while our scale parameter is around 7.8. Of course, we conducted two different error analyses to find more consistent result. The first of which is R square, and the second is RMSE. We want our R square value is the large and the RMSE value bit small. As seen here, our three functions almost sit on top of each other. Because our wind profile is very smooth, the wind profile of our region has close to each other and around 2. And we see a single peak in distribution. Here the method with highest R square and lowest RMSE values is the maximum likelihood method for 65 meters. We see the same features for 95 meters with the methods we already use, and because we use the Hellman equation, our shape doesn't deteriorate much and there is no distortion because we use the Hellman coefficient. Therefore, we think that the results will be in favor of the modified maximum likelihood method within the three heights. Again, in the highest R carre and lowest RMSE value for maximum likelihood method. It's possible to say the same things within a 120 meters. As you can see, the method highest R squared and lowest RMSE is the modified maximum likelihood method. When we calculate the capacity factor by putting these results in their place, we have obtained results around 0.32 for the 1 megawatt turbine, around 0.39 for the 3 megawatt turbine, and 0.46 for the 5 megawatt turbine. As can be seen here, the 5 megawatt turbine gave the highest result. It has been observed that 1 megawatt turbine can produce around 2,800 megawatt hours, 3 megawatt turbine can produce around 10,000 megawatt hours, and 5 megawatt turbines can produce around 20,600 megawatt hours. In the light of all this, it can be said that the most consistent method for this study is the modified maximum likelihood method. The highest capacity factor is provided by the 5 megawatt turbine, and in addition to this, the annual energy potential have been determined very close to each other. Therefore, the turquoise region has enough potential to build a wind turbine. Finally, in addition to the socioeconomic benefits of the wind turbine to be installed, it will also contribute to the goal of reducing carbon emission, increasing the production of electrical energy, and also reduce foreign dependence in energy. And there's my references. Thank you for your attention. Here's my contact information. You can contact me for any question. Thank you.